Math 1343, testing means, testing two population means the p-value approach. Now, you may or may not have watched the previous video and seen the previous problem. And although it's not necessary to do that to follow this video, it will put it in a little more context. But I've decided to do this video, absence of context, to emphasize the technical flow of this hypothesis test. And at the end, we're going to get the same results as before, which was that unpolluted land yields more potatoes on average than polluted land. Imagine that. But what I've done up here is two things. Number one, I've briefly summarized the p-value approach in general, state the hypotheses, calculate the test statistic, get the p-value, and then make a decision. I left off the answer the question step since there's no context here. And I also extracted some of the information from the previous problem. Null hypothesis that the two different types of land yielded the same mean potatoes per acre. Against the alternative that the unpolluted land had a greater mean average than the polluted land. Again, it didn't say that up here, but that's where those hypotheses came from. And I also recorded all of the sample data that we had. In our 30 acres of unpolluted land, the mean yield was 10.2 tons per acre with a standard deviation of 0.35 tons per acre. But in our sample of 12 acres of polluted land, the mean yield was 8.1 tons per acre with a standard deviation of 0.24 tons per acre. And I did explicitly say that the significance level was 5%. But again, if you're not given a significance level, you assume it's 5%. I wanted to go through the calculation of the test statistic again and the translation of the test statistic to the p-value. But first we need to remind ourselves that this is going to be a two-tailed test, right-tailed test, because the alternative hypothesis says greater than. That will be important when we go to calculate our p-value. All right, so to calculate our test statistic, so here's step one. To calculate our test statistic, we go back to the same formulas as before. I will rewrite the formulas so that they're contained in this video. Our standard error was the square root of the sum of the ratios of the squares of the standard deviations to the sample sizes. So there's your formula for standard error. And when we put those numbers in, we had gotten 0.35 squared over 30 plus 0.24 squared over 12, and all that was square rooted. I don't remember what that value was, but there's no harm in calculating it again. 0.35 squared divided by 30 plus 0.24 squared divided by 12 equals, and then square root that. I remember that number. To 4 decimal places, we got 0.0943. It was actually 425, but the 5 rounded the 2 up to a 3. And for our test statistic, the formula was the difference in the sample means x bar 1 minus x bar 2 over the standard error, with emphasis that the order of these subscripts needs to match the order of these subscripts. Otherwise, you'll have the wrong tail and everything will go crazy. Our first sample mean was 10.2. Our second sample mean was 8.1. Our standard error was 0.0943. And I remember we got a really large number. It was like 22 point something, which in some context is not a large number. But in terms of Z's and T scores, 22.2694 is a crazy large number. But what do we do for step 3? For step 3, we calculate the p-value, and the p-value is the area of the tail cut off by the test statistic. This test statistic is way off to the right. And we're cutting off a right tail because it was a right tail test. T equals 22.2694. And now we need to figure out this area. And when we find that area, it will be the p-value. We don't have to double it because it's not a two-tailed test. But the problem with finding the area here is the same as it was 2 videos ago. The t-chart is great for finding t-values, horrible for finding areas. In order to find the area, we first have to go to the correct row, which means we need to calculate the degrees of freedom. The formula for the degrees of freedom, and since it's not in this video, I'll write it up here, is the minimum of N1 minus 1 and N2 minus 1. So basically, you go for the smaller sample size and calculate its degrees of freedom. Smaller sample size is 12. 12 minus 1 is 11. So we would go to the 11th row in our t-chart. Now give me 1 second, I'm going to recreate this. 0.10, 0.05, 0.025, and if you're wondering where these numbers are coming from, they are just the numbers on the top row of the t-chart, which those 6 numbers I have memorized. What I don't have memorized are the t-scores associated with each of them. So I'm going to unplug my phone from my computer because it's charging up my phone. Make sure the video didn't stop. Still good. And I'm going to drag my computer over here because it's got the t-chart on it. All right, so if I go to the 11th row, from left to right, the t-scores are 1.3634. Normally you wouldn't write these down, but I want them to be in the video. The next one is 1.7959. The negative of that was our critical value previously. Not the negative, just that. Next one is 2.2010, 2.2010. The next one is 2.7181. The next one is 3.1058. And then the last one is 4.0247. And I want to remind you what we do here to find the p-value when we're using the t-chart. We need an area. The areas are what are on top of this. Recall that in the t-chart, these are right tail areas. And down here are your degrees of freedom. What we have is a t-value, so ideally we want to look in the correct row based on the degrees of freedom and locate this t-value, but guess what? It's not there, not even close. So how do we find the area of the tail and hence the p-value? Well, you find bounds, or you find a range for the p-value by finding the t-score that our test statistic is between. So, which of these two numbers is 22.2694 between? The answer is none of them. All of these are way smaller than our test statistic, but that doesn't mean we can't say something. Our test statistic is over here somewhere. We'll put test stat over here. And so what would its area be? Well, we don't know what it is, but we can put some bounds on it, because notice what's happening in these areas is that they're getting smaller and smaller as we move to the right. So if our test statistic is to the right of the last column, that means that its area just keeps getting smaller, and it's smaller than that last one. So when you're looking for an area of the tail for a p-value, and you go off the chart to the right, then you know that that area and hence the p-value is less than this. So what we can say is that the p-value, let me write area equals p-value there. The p-value is less than this area. Again, you can draw that conclusion because as you move from left to right across the t-chart, the areas are getting smaller and smaller, and we have to move further right to locate where our test statistic was b, since it's greater than this number here. So we don't know the p-value, but we have a range for it. So what does that get us? Well, recall that when you make your decision in the p-value approach, if your p-value is less than your significance level alpha, you reject the null hypothesis. And if your p-value is greater than or equal to the significance level, you don't reject the null hypothesis. Recall that the p-value is actually the probability, it's essentially the probability of this happening if our null hypothesis was true. Well, if our null hypothesis was true, then the probability of this happening is less than 0.1%, highly unlikely. And so we blame that discrepancy not on the samples that we picked, but by the fact that our null hypothesis is wrong. And that's why we reject a null hypothesis when our p-value is less than our significance level. So our fourth and final move is to reject the null hypothesis, which was the same decision we made last time when we did the critical value approach. So we would reject a null, Yes, we would reject the null and we would accept the alternative in its place. All right, so the p-value approach for testing means is not my favorite, but I do want you to understand what p-values are and how to calculate them, even with the t-chart. Honestly, the best way to do the p-value approach is with technology, but since I'm not requiring everybody to have the same technology, we'll just continue with the t-chart approach. And that wraps up this week's videos.